For decades, our entire digital world has been running on this incredibly powerful engine. But that engine has a really big flaw. It's basically a machine with no brakes. Today, we're going to break down the story of Rust and see how a whole new set of rules is creating a much safer digital future for every single one of us. So, to really get this, you have to understand that C++ is, well, it's pretty much everywhere. The operating system on your computer, the browser you're using to watch this, the most complex video games, the biggest financial systems, it's all built on C++. It's the language of raw performance, giving developers total control. It's truly the bedrock of modern computing. The thing is, all that control comes with a huge catch. In C++, the developer is personally responsible for managing every single piece of memory. One tiny mistake, one little thing you forget, and you can have catastrophic system failures and massive security holes. Imagine you're a race car going flat out, except you also have to build the brakes while you're driving. That's C++. Alright, so let's dig into that idea. Let's look at this high-stakes world and the exact problem that Rust was designed to solve once and for all. For the longest time, developers had this really tough choice. You could have a safe language, but you'd have to give up speed, or you could get the raw power of C++, but you had to live with the constant threat of these memory errors. Rust comes along and says, why not both? It delivers something called zero-cost abstractions, which is a fancy way of saying you get the speed of C++ with the guarantees of safety. Okay, to really get this, you have to see it in action. Let's walk through one of the most classic and dangerous errors in C++, the use after free bug. It's all caused by something called a dangling pointer. Okay, so it all starts out pretty simple. A program needs to store some data, let's say the number 42. The computer sets aside a little chunk of memory at a specific address and puts the number there. Easy enough. Alright, step 2, we create something called a pointer. You can just think of it like a signpost. The pointer itself doesn't hold the number 42, it just holds the address of where to find it. It just points the way. Okay, and right here, this is where things get really dangerous. The program is done with the number, so it tells the computer, hey, I don't need this memory anymore, you can have it back. The computer frees it up for something else. But, and this is the crucial part, our signpost, our pointer, was never told. It's still pointing to that exact same spot, which is now empty and invalid. And boom, that's the clash. Later on, the program follows that old dangling pointer, thinking it's going to find the number 42. But instead, it finds who knows what. Maybe nothing, maybe garbage data, or even worse, maybe another program's secret information. This is a use after free bug, and trust me, it's the root of so many security nightmares. So, how do you stop this from happening? Well, you could try to have armies of developers check every single line of code, or you could just change the rules of the game entirely. And that's exactly what Rust does. And that brings us to the hero of this story, the borrow checker. Now, this isn't something that runs while your program is running. It's a core part of the Rust compiler itself. Think of it as this super smart, super strict referee that analyzes every memory access in your code before it can even become a program. It enforces these really strict rules about who owns data and who's just borrowing it. So let's run that same exact scenario, but this time in Rust. The second our code even tries to create that dangerous situation where memory gets freed but a pointer still exists, the borrow checker just steps in. It sees the potential for a dangling pointer and says, nope, not allowed, stopping the bug before it's even born. And this is the magic wave here. You don't get a random crash that some poor user has to deal with. You, the developer, get a clear error message. The code won't even compile. Rust doesn't just help you find memory bugs, it makes a whole category of them, literally impossible to wait. Now, this isn't just some cool academic idea. This one feature is causing a massive shift across the entire tech world. I mean, just look at this number from Microsoft. 70% of all their security bugs are memory safety issues. That is the exact problem that Rust just solves. And you better believe the big players have noticed. We're not talking about some niche language anymore. We're talking Amazon, Microsoft, Google, Meta, all of them are rewriting critical pieces of their infrastructure in Rust, specifically for this guarantee of safety. But maybe the single biggest vote of confidence came when it was adopted by the Linux kernel. Kernel is the absolute heart of millions of servers. It's inside every Android phone, it's everywhere. And after years of careful testing, Rust was officially welcomed in, a space that for decades was basically fee-only territory. And you can see this happening in real time. I mean, Rust was literally born at Mozilla to make the Firefox browser safer and more stable. Today, nearly 10% of that huge codebase is now Rust, as they systematically replace the old, riskier C++ parts with safer, new components. So, what does this all mean? What does a future built on this new, safer foundation actually look like? For decades, right, writing this kind of low-level code has been this constant battle, always managing insane complexity and wrestling with these hidden dangers lurking in memory. We're finally starting to move beyond that. But what's so cool is that Rust's rules, enforced by that borrow checker, they're not a cage holding developers back. No, they're more like a scaffold. They give you this incredibly strong, reliable structure, these unbreakable boundaries that actually let you build even bigger and more ambitious things on top. And that's what you get. When you take away that constant fear of memory bugs and data races, developers can finally focus on what they do best, building amazing things. They can innovate without constantly having to worry about the ghosts of C++. So look, this is so much more than just a new programming language. It's a fundamental change in how we build our digital world. From the cloud to our phones to the very core of the internet, the foundations are being rebuilt with safety guaranteed. The future is memory safe. The future is Rust. So I'll leave you with this. For the first time, we can build the absolute bedrock of our digital world with a kind of mathematical proof against its most common failures. The question isn't, can we build it safely anymore? The real question is, what incredible things are we going to build next?